Good morning, everybody. So our topic, as you can see, is machine learning and cybersecurity. We worked with ATC, Architecture Technology Corporation. They're our sponsors. I am Sam Boyer. It's Devonte Bell over there. This is Blair Panic and Igor Mektiev. Our mentors at ATC were Vic Thomas and Jordan Bonney. And although he wasn't technically one of our mentors, Fabio Pazzo is another ATC member, and he was a huge help throughout the whole process. So figured I'd give him a special mention. So a lot of this is kind of similar to what we did in the midterm. So the company overview of ATC, they create and design real-world systems and do a lot of network research, and they pride themselves in being able to pursue a high-risk, high-reward approach to get customers advanced systems. They're a privately held entrepreneurial enterprise, and they have a very flat corporate structure, and that's because they're basically a research organization. So there's not departments per se, there's more just a lot of different extremely talented individuals working on different tasks, different projects, things like that. So their core technical areas, you can read through those if you want, but the ones that are most pertinent to our project were next-gen networking and cybersecurity. So the need that our project is filling is exploring the realm of intrusion detection systems, or IDS. So these are devices or pieces of software that monitor networks or individual machines for suspicious activity. And these are necessary and widely implemented in organizations of any significant size. So we really had to add novelty to our project. And the novelty is basically how can we improve upon traditional IDS systems. So the novelty that we were approaching, that was our assigned project, is using machine learning in intrusion detection. So machine learning, for any who are not aware, they're really complex algorithms that use matrix multiplication, statistical analysis, gradient descent calculation, things like that. These are extremely efficient algorithms that can be used for classification and a lot of different things, but the beauty of computers is that they can do all the heavy lifting and calculations for us. And the reason why this is important for us is cybersecurity is still largely untouched by machine learning. The number is 25%, so by 2020, only a fourth or 25% of all IDSs will use some form of machine learning in their processes. So this project was really kind of on the cutting edge of research. So our schedule, our sprint 1, we underestimated how much time we would actually spend. We underestimated, and that was by quite a bit. We went 70% over what our original estimate was. Sprint 2, we then overcorrected and went and significantly overestimated. And then sprint 3, for reasons that we'll kind of explain, we found a lot more work to do in sprint 3. So that one, it's all getting closer to 100%, but we never quite got there. So again, overall architecture, this is the same as the midterm as well. There are 3 primary components. There's the development environment, and that's just so that we're all working in the same OS. The data parser module, that's generating the testing and training sets for the machine learning. And then there's the machine learning IDS itself, which is the script or the model. They're the model that's actually doing the machine learning. So now I'll pass it over to Igor to talk about the development environment and the data parser module.
All right, so as mentioned in the midterm, we have several components, and one of the main ones is basically the development environment. I will not go too much in depth, but the main idea is we have a virtual machine provisioned using Vagrant and Ansible scripting that pretty much creates and installs all the scripts necessary for the developers and future developers to use, which pretty much makes it a consistent development environment. And if there's any one of the changes in one of our teammates, we can propagate that to everyone, and everyone's on the same page, everyone's using the same libraries. So that takes care of that issue when you say it works on my machine, but it doesn't work on production. So one of the main modules would be data parsing. So the idea was we take the data sets from MIT Lincoln Labs and DARPA, and we need to take that raw data with the metadata and process it, correlate the data, and basically create a training data set for the machine learning model. And this is just a recap. This is what the metadata look like. There's on the left side, you have a start date and end time of the event, the duration, what kind of service it's using, source IP destination, and a potentially classified attack with percentages. So it could be RPC, execution, guess passwords, and so on. And then we have the raw data, which is basically raw packet data taken from the TCP dump. As turned out, the the real world data we will be using to actually train the data, not the sample data, was about like half a gigabyte or something. So it's pretty large data set. So after the midterm, we have certain challenges which kind of we were faced with. The large amounts of data, so they come anywhere from 500 gigabytes to a terabyte. We also found out that the metadata was inconsistent. Not only the dates were not really specified which time zone they were, we had to guess to figure that out. And then the real data sets that we're going to be training on, not a sample data, which was really, really small, the dates were actually inconsistently specified. So some of them were 1998, some of them 98, some of them was a month, date, year, some of them year, month, date. So in order to clean that up was kind of that was a challenge in itself. Also, another challenge was that the events were inconsistent and non-sequential. So, for example, the first event would start at time 0 and it will span a day, and another event right after would start again at 0 but only last a minute. So in terms of parsing, that was the challenge itself. So we had to kind of restart from scratch every time we would parse an event to collect that data. Also, the Python library we were using, which is dpacket, did not support seeking. So you could not just jump to the time frame you needed to. So if you have a week worth of data, you'll have to kind of start from scratch and read it packet by packet. And we also changed our approach from the midterm. We're no longer using EditCap program to split the files into manageable chunks because it was just too slow to run. It would run more than 24 hours or 2 days just to parse the file, one of the larger files. So our final solution was, after doing about 5 or 6 different scripts and trying different things, was to load the whole thing into RAM, use many threads, and it becomes really fast-ish. About 3 hours for about 2 days worth of data, which is pretty fast considering it actually finishes. And now I will pass it to you.
Yeah, I'll take back over here. So basically a week after the midterm, we actually discovered that CSVs generated from these DARPA data sets already existed and they were publicly available. So this was a huge kind of forehead slap moment. Oh my gosh, we can do so much more now. So this is actually really great because it allowed for more work to be done for the rest of the team. I mentioned Sprint 3, you saw a lot more work, and it's because we actually had more things to do. We allowed for more specialization. So team members could focus more on machine learning, other team members could focus on generating our own CSVs, and other team members could work on editing this CSV for actual testing on the machine learning. So there's a lot more things that we had available to us to do. So the new task for this gigantic CSV with all this data was to first kind of split it up to create a library of attacks, and then map all the non-numeric values to integers, and then you can create the custom data sets with whatever desired ratios, like 50% normal traffic, 10% nmap traffic, 50% or 10%. Yeah. So just an example of the mapping process. So we have a record here, and you can see TCP, that's your protocol, HTTP, that's your service, SF, those are the flags related to that session, and then normal at the very end there, that's the type of traffic, that's your label. So that goes through a mapping process, which basically was just gigantic dictionary files or dictionary objects. So you're mapping all of these different non-numeric values to numeric values. So if you see after the mapping process, normal is associated with 0, TCP is associated with 0, HTTP is associated with 0, but say you have FTP or UDP or something like that, those would be different values as well. So that's kind of what the mapping process consisted of. So now I will pass it over to Blair, and he can talk about the machine learning.
So originally, we're still using the Python TensorFlow framework for the machine learning processing. We did get the resource with Martin Gorner. We did have some issues with the data that they used for structuring it into a tensor was actually in bytes rather than digits, where the KD99 format we had was in digits. So we had a kind of a large struggle figuring out how to do that or build our own tensor. So we use Martin Gorner's version more so as like a helping hand rather than a guide. And then I actually found another TensorFlow guide online that I used to actually format what we needed and used Martin Gorner's version more so for the categorization of different types of attacks into the final nodes of the machine learning. Then we'll have a demo here. So we're loading 98.57%. Just kidding. So we actually have picture demos. So the first portion, the top, this is kind of how TensorFlow formats the different tensors that you use to feed into the actual machine learning software. So the top, as you see, so there's an ordered dictionary. The first label is the actual feature, so the duration right there. So that's actually a long list of all like many durations. So you can do it in different batch sizes, which we did it in 40. So that has 40 different values of durations, and then it builds a tensor of all of the different features. So we had 41 features. So this would be a matrix of, or each session, right? Each array inside is 41 in length, where it's the 41 features followed by the value of whether, like, what type of attack it is. And then this is what happens when we actually run it. So we do 500 iterations, and every 10 iterations we had it print out how much is being lost and then the actual accuracy. So, you know, clearly you see it kind of jumping up and going down a little bit and then coming back up. But this is all for the training data set. This is what it's being trained on for the actual data. The last set is basically our script not knowing the actual values of the attacks and then comparing what they are to what the machine learning script thinks it is. And then that's the accuracy that we get at the end for 98.57%. And then I'll pass it over to Devante to talk about some goals and accomplishments.
So some of our goals since midterm, obviously, were to create a library of attacks from the DARPA data sets. And then to use that library of attacks to create custom data sets with specific ratios. So I know when we first came to ATC, they kind of focused on DDoS attacks. So we had normal traffic, 2 DDoS attacks, and then
3 DDoS attacks.
3
And then
DDoS
2
attacks.
probing attacks.
And then, yeah. And then, so from that, we created the machine learning script that has the 98% accuracy. At first, when we first created it, it had like a 56% accuracy rate. And then we were able to kind of tweak with the learning rate and other instances to make it that accurate. And then just the ability to create CSVs. So it indicates that it can potentially have a live environment for implementation. And then some issues and risks we ran into. This is kind of pretty much similar to the midterm. We had no current knowledge of machine learning or TensorFlow, so a lot of the beginning sprints were tutorials and examples just going through online, a lot of reading. As far as the data sets, combing through all the large data, and like Igor mentioned, pulling out relevant information and the fact that all the data was kind of different formatted, that was really annoying and an issue itself. And then our third issue was that our project is more of a research project compared to most of the software development. So kind of fitting that into documentation was a challenge itself. And then our last issue would be the 5 different scripts just to parse the data. And a post-mortem summary. So the first is just touching on the fact that it is a research and development project, and we're trying to fit it in software development type documentation. We found that it was pretty hard at the beginning and kind of frustrating, but after emailing the professors numerous amount of times just to check with like if we were doing the right class diagrams, if it was fittable for our project, The machine learning was an undertake, but it's worth a challenge, or it's worth the fun challenge. So that's just touching on, you know, us not really understanding machine learning at the beginning, but then, you know, it's really cool to see how our model actually works at the end, and it's cool to go online and see all the different type of examples that they have that they use for machine learning, and just to be understanding those. And then machine learning is 90% data manipulation. So our first 2 sprints were pretty much all data manipulation. And then, like I said, our model at the beginning was about 56%. I know Blair was able to fix that within hours to get that to 90%. So that just kind of gives you the scale of really how much the modeling to data manipulation is in machine learning. Then all things considered, just ATC's relaxed approach to the project. We were kind of worried about this at the beginning of our project. I know it was kind of unclear really what the project was, not really having a good background. But in all, we're really appreciative of ATC's relaxed approach to kind of let us really do whatever we feel is fit for our project. And then we'll go back to Igor on the next steps.
All right. So I guess since we're able to actually extract all the necessary data and generate the CSVs and training data, so the next steps for our project, could be used for creating a live environment for this particular problem, which was kind of a stretch goal for us. We just wanted to, ATC really wanted us to have, something delivered using synthetic data, but now what we're going to give it them will be really a final script which can generate the real training data off the real data, and which can then be plugged into the live environment. So what we can do next is CSV generation could be certainly improved. So right now we're sitting about 3 hours to generate about 450,000 events. So this can probably be narrowed down easily to less than an hour for sure. And we will be providing them a solution. There's a way to index this data and bypass the problem of not being able to seek to a particular point in time to location in this gigantic file. So, and then, so the further steps we can take is we can plug in. So once the model is generated using the live data, which we can approximately extract right now about 13 different features as opposed to 40 that DARPA document had, but that can be easily improved by simply sitting down and figuring out what is relevant for a particular attack. And then in the live environment, what's going to happen is we can easily run a cron job and take snapshots about every 15 minutes for like a few seconds of traffic, and then just feed it in the model and just generate whether or not this is a particular attack or not. So this is going to be a really, really easy thing for them to take this project and just build on it. And since we're using Python and all the open source libraries, it's just a no-brainer. It can run pretty much on any platform. So, yep. And obviously to notify our admin is just a send mail command. It is done. And questions?
So if you TCP dump like into a PCAP, then your script, you've got scripts to convert that into the data you need that your model will analyze?
Yep.
Yeah.
It splits it into records with the features basically just in CSV format, basically.
Have you guys attempted simulating attack and testing it if it picks it up?
We didn't get to a live environment implementation, but those DARPA data sets, they do all those include simulated attacks.
Yeah, not just that. At the bottom of the script, you can also add in your own prediction with the same amount of features for random numbers that you pass in to the script, and then you basically know the probability, or you know what type of attack it is, and then you just throw that into it, and then you'll actually simulate, yep, it does actually know what type of attack this is as well. Yes.
What percentage of your data is test data and what percentage is training data?
So we actually did pretty uniform distribution. So it's 10,000 records for the testing data and 10,000 records for the training data. And then, like we said, 50% of both is normal traffic, and then 10%, the remaining 10% segments are different attacks. So
You had a question in the back.
You mentioned having problems seeking in a CSV file. Was a database?
So no, so it was not an issue with seeking in a CSV file. So the problem was really seeking inside of a PCAP file, and the dpacket library, what it gives you, it's pretty much a for each loop, which you have to loop through every single packet and extract the data. And so you couldn't really, there was no facility to actually say, go to this timestamp. So my solution was actually at the end, which I didn't have a chance really to finish, was just, since we're already loading the stuff in the memory, which is not a big deal, it's about 500 megabytes, and it's not a big deal again. What we did was you can just use like an iSlice, and using an index, and just kind of literally slice it up in memory and just jump in there. So that would pretty much solve that issue. But
Would a database make it easier, do you think?
we thought about that and using like something like a SQLite, but the fact that it's already so fast and it's within less than a second and parses like around 50 attacks or so, I think the overhead of database might be a little bit slower than actually running it already in memory, like using in-memory manipulation. So, but yeah, that was definitely something mentioned either by ATC, and I'm like, let me try a SQLite. And I'm like, wait a minute, I'm already in memory. It's going to be slower seeking that file all the time.
Any questions? Yes.
Is the data imbalanced?
imbalanced.
Yeah, I mean, yeah, this kind of data, normally it's negative is most of the data, but the positive is just a small part. I mean, you have a lot of traffic, yeah, but just a small part of maybe, one person is attacked, yeah. So
Oh, right,
the
yeah.
other is not.
Yeah, right. The testing set is certainly unbalanced. We wanted to make sure that we could classify specifically. What would have been a better implementation would have been the testing set would be that 99% or so normal traffic data, just because we wanted the training set specifically to have the attacks that we want to be able to detect, and then just for ease of use, we balanced it just mirrored. Yeah, right. And what you're saying is true. In a real live environment, it would be 99.99 real data,
Yeah.
or real normal traffic, right? And then just a tiny little bit.
Of actual
Attack.
attacks. Yeah.
But we just wanted to be able to give a solid percentage on these attacks are detectable consistently. That was kind of our idea.
And it was a proof of concept as well. So
Okay, you mean the test data also balanced in your testing?
Yes.
Yep.
Just a general comment, we could make a fusion metrics for like false positive, true positive, false
Oh.
positive.
Ooh, yeah.
Right.
That'd be good too. Yep.
Yeah, we also explored with trying to get
That's a portion
accuracy.
of that's a portion of loss as well. So basically, that's what it means by loss. Is it actually loses the correct categorization?
So and that's something we explored doing too, was getting individual accuracy measures for each individual attack. But again, we just kind of ran out of time to add that towards the end here. So that's definitely something we could explore as well.
So I really like this. I was kind of pretty impressive. Can you just talk about the cyber range and how this might fit into what the goals of
Yep.
ATC really are?
So some of the future things that they could do with this type of software is they can either use it. So what the Cyber Range is it's a platform or a virtual machine box that you can like log into and actually take courses on. So it's almost like online school kind of, or taking modules that you paid for. What they can do is they could run this on a virtual machine and then have someone attack it and try to see if this software or if this machine learning script will actually detect their version of an attack and spit out a message saying, hey, the system's being under attack, because it has multiple clients and users. Yes.
With having it be an open project like that, do you are there any concerns about a potential attacker modifying one thing and testing it against, like, finding out what doesn't, or
What does get
detected?
passed or what
Yeah.
doesn't get detected. So that's the actually like the objective of machine learning, right? Is sometimes things do get lost and do get by it, but the system admin is still technically, supposed to be monitoring and seeing stuff. But as well as the machine learning still should be learning as well. So it should still be, hey, this is an actual attack. So the system admin will actually stop the server. So you could probably add something there when the system admin actually does say there is an attack. Then the machine learning script will be like, oh, I missed that. Let me throw that in so I can learn from the system admin as well as the program itself.
That also has to do with attacks change every day, right?
Yeah.
Because these data sets are from 1998. These are extremely old attacks that we're training on. No one's actually going to try to use one of these attacks to.
Just because there's
Create
so
an
much things
organization
to
anymore.
stop them
Right.
already, right?
So-
And technology is constantly advancing, so it's kind of a circular loop in most senses where there's new computers, new technology, so there's always going to be a way to attack and defend.
So in order to get this more, usable to defend against these more novel attacks, you probably, just like any piece of software, you have to do updates regularly to retrain the model. So.
Thank
Awesome.
you.
Thanks, everybody.